guys, you really have got to have this down before you go into calculus. It's going to make your life so much easier. So we are going to be using trig identities to simplify things. So what is a trig identity? An identity is something that can just be written as something else. So we can use these identities to rewrite these in different formats. So you already have these on your paper, you know, the trig identities. You don't need to write them down. We're trying to save time so we can start practicing. So we should have these memorized. So we know that sine of u equals 1 over cosecant. Cosine of u is 1 over secant. Tangent of u is 1 over cotangent. Cosecant is 1 over sine. Secant is 1 over cosine. Cotangent is 1 over tangent, right, everybody? And then here's the important ones. Tangent of u equals sine over cosine. So tangent is sine over cosine. Thus, cotangent is the reciprocal, cosine over sine. Please try to get those down in your head, like take a screenshot. Okay, those are called reciprocal identities, which makes sense. Cosecant is the reciprocal of sine, and so on. Now these are called Pythagorean identities. So these may be new to you. So what I did here was write down the original identity. Sine, you use this, I literally can remember vividly sitting there in calculus 2 and using this identity. I can remember exactly where I'm sitting. Yeah, exactly. You can. So now you're not going to say that because your brain's more advanced and you're more mature. Well, more advanced. So here we go, guys. This is the original identity. Sine squared u plus cosine squared u equals 1. So if you ever have sine squared x plus cosine squared x, it can be rewritten as 1. They're equal. So you can take this identity, guys, and think about it. You can subtract cosine squared u from both sides of the equation, thus sine squared u is equal to 1 minus cosine squared u. So this is what I call like a byproduct of the original. Does everybody understand? So if you ever have if you have 1 minus cosine squared u, it's the exact same thing as sine squared u. And then here's where we're trying to go with identities. So a lot of people say, I just don't really see like where you're trying to go. What we're trying to do is we're trying to get things down into pretty answers. So for example, I just want to show you so that you understand where we're going with trig identities, because then it'll make it easier. For example, do you see how this would be a prettier answer than this? Like this would be a prettier answer than this, like, and so on. Like, look, this would be a prettier answer than this. Do you get what I'm saying? So that's like where we're trying to go with this. So for example, if we have this, do you see how there's two terms? This is considered a prettier answer because there's just one term. Does that make sense? Because then it helps you see where am I going with these identities. So cosine squared u, if I subtract sine squared u from both sides of the equation, then cosine squared u would be 1 minus sine squared u. And this would be a favorable answer over this because there's two terms here versus one. So that's just kind of where you're trying to go with trig identities. Taking something that's split apart and putting it into one answer. The prettiest answer possible. See, this is the other trig Pythagorean identity. 1 plus tangent squared u equals secant squared u. So 1 plus tangent squared u equals secant squared u. So this is the original, and this would be a byproduct. So if we subtracted 1 from both sides of the equation, tangent squared u equals secant squared minus 1. And then if we also subtract tangent squared from both sides, 1 equals secant squared minus tangent squared u. So I want to get your brain seeing like what would be considered the favorable answer. There's two terms, so this would be favorable. If you had this, you would want to rewrite it as this. Does everybody see why I'm saying that? So isn't this more favorable than that? And then also this is obviously more favorable than that. Does everybody see what I'm saying? Okay. Yes. Just like x, any variable. So we have another Pythagorean identity. 1 plus cotangent of u equals cosecant u. 1 plus cotangent u equals cosecant u. So then a byproduct of that would be subtracting cotangent squared from both sides. And so 1 would be cosecant u minus cotangent squared u. It should be squared, no wonder. Let's fix that real quick. Squared. So then also, if we subtract 1, cosecant u minus 1 is cotangent squared u. So the favorable answer would be this one, because there's only one term. Favorable answer would be this one, favorable answer would be this one. So that's where you're going to go with these trig identities, is what's the most favorable answer. Okay, these are called co-function identities. So sine of pi halves minus u equals cosine of u. Cosine of pi halves minus u equals sine of u. Tangent of pi halves minus u equals cotangent u. Cotangent of pi halves minus u equals tangent of u. Secant of pi halves minus u equals cosecant u. And cosecant of pi halves minus u equals secant u. You already have those memorized from previous years? So you guys already know where they come, like why that makes sense? Do you want to talk about why that makes sense? Okay, let's do an example of one. So, if you want to make sense of it, I just did one that made sense. So to make this, like, why does this identity work? Let's think about why. So for example, let's look at, here's my unit circle, I'm going to push it up there. So if I said to you, sine of 60 degrees, you'd say, what's my answer? What's sine of 60 degrees? Sine is y, correct? So it's root 3 over 2, correct? So we're told that sine of pi halves minus u equals cosine of u. So let's plug that in. So instead of sine of 60, let's think of it as sine of pi thirds. Everybody understand? Yeah. So sine of pi thirds equals square root of 3 over 2. Okay. So can I erase some of this to give myself some room to write? Okay. So here we go. We're told that sine of pi over 2 minus u equals cosine of u. So let's look at this. So sine of pi halves minus pi thirds. Let's deal with pi thirds. Everybody good with that? So minus pi thirds. I'm just randomly picking one. Equals cosine of pi thirds. Let's see if that's a true statement. So isn't this the same thing as what is pi halves minus pi thirds? Yep, so sine of pi 6 will be equal to the cosine of pi thirds. Let's see if that's a true statement. So sine of pi 6, where's pi 6? Sine is y, correct? Yeah. So we have 1/2 equals cosine of pi thirds. Find pi thirds, cosine is x. So that's why that works. Yeah. Good, okay. So we could go through and do that with all of them, but we don't need to. Okay, here's the even odd identities. So remember that sine is considered odd, tangent is considered odd, and cosine is considered even. So remember, for an even function, if you have original function f of x and you take that function and plug in negative x, plug it in negative x. If it simplifies to be f of x, the original f of x, it's considered even, correct? And then if we have a function f of x and we plug in f of negative x, algebraically, if it simplifies to be -1 times f of x, that's considered odd. So we have talked once about that with how that works. So explore that on your own time of why sine is considered. Do we need to explore it? No. That just says odd. Well, it takes us 2 seconds. What's sine of negative? So let's say we're dealing with sine of 30 degrees, okay? So sine of 30 degrees, so now instead we're looking at sine of negative 30 degrees. Plugging in negative. So what's sine of positive 30 degrees? 1/2. Now let's look at sine of negative 30 degrees. So what's negative? It's -1/2. So didn't it come out when we plugged in the negative of that? It came out -1 times the function. So that makes it odd. The original one's 1/2. Right? Sine of that. So when we plugged in sine of negative 30, we got -1/2. Didn't our function simplify to be, or the answer was -1 times the original, which makes it odd. So sine and tangent are odd, cosine is even. Because look, if you plug in, if we look at cosine of 30 degrees, we get square root of 3 over 2. Let's also look at, let's plug in negative 30 degrees for testing if it's even or odd. So what do we get out? Square root of 3 over 2. So do you see how when we simplified it, there was still f of x, original f of x. So that makes it even. So odd, odd, even. So that means sine of negative u will equal negative sine of u. So if sine is odd, so is cosecant, because they're reciprocals. Cosine of negative u equals cosine of u. So secant of negative u equals secant of u. Tangent of negative u will simplify to be negative 1 times tangent of u. Cotangent of negative u is the same thing as negative 1 times cotangent of u. Here we go. I think I'm going to start right away. Simplify the trig expression. Here we go. Simplify the trig expression. So the first thing I do here is you just kind of got to go for it. Like, you have no idea where to start and kind of no idea. Like, there's many ways to do it. So guys, understand the one way I do it in here does not mean that's the only way. So a couple things I just want you to notice. These are just the things I'm noticing. Literally, I could do this totally different next hour. Sine, and you might see it different than me. Don't we have a sign in each term? Yeah. So I'm going to factor out sine of x. So now I'm going to write what's left in my parentheses. So sine of, no, there's no equal sign. We're simplifying these. So what's going to happen in calculus is you're going to be asked to do something with this. The calculus, do it with this, and you're going to want to simplify it to something a little bit prettier. So we're literally taking this and using trig identities to make it a prettier answer. Does everybody understand what we're doing? Yeah. We're simplifying it. Just like if we were to do 4x divided by 2 is 2x, that's a prettier answer. Okay, here we go. So I factored out a sine x. So then divide both terms by sine of x. Your algebra's got to check out. Cosine squared x minus 1. So then you look at that and say, can I continue to simplify this? You sure can. What is this equal to? It is equal to sine squared x. So rewrite it. So we now have sine of x times by, instead of cosine squared x minus 1, we rewrite it as sine squared x. So isn't my final answer going to be sine of x times sine squared x is sine cubed x? Yeah. So literally they're equal answers, guys. This is just an ugly form of it. This is the pretty form because there's only one term. No fractions. Yeah, you just gotta memorize it. Trig identities. This is 30 out of the book if you're interested. Sine of x times sine squared x is sine cubed x, or you could write it like this. Sine of x cubed. Same thing. Sine squared x just means we have 2 sine of x. Because there's 1 sine of x times x squared. It is x cubed. Sine of x times sine squared of x is how many sines? 3. Does that make sense? So they just write it like that. They put the 3 here, but it means the same thing as this. Yes? So like, what? Because remember how I had all those byproducts. You can use the byproducts. So the original identity is actually this. This is the original identity. So then we have these 2 byproducts. That's the opposite. That's 1 minus 1. Oh, was it? Are you sure? Okay, well, let's think about algebraically if it's the same thing. So let's factor out. It's not. It's not the same thing. No? Yeah. Just a sec. No, I know what you're saying. So let's talk about it and algebraically figure out what it's equal to then. So we've messed up somewhere, which is okay. We can fix it. So we've got to just look at this and say, what is this? So couldn't we? So good point. Let's look at it like this instead. Isn't this the same thing as, let's factor out a negative 1. Yeah. And left is negative cosine squared x plus 1. Which is negative 1 times 1 minus cosine squared x. That's a good point. We needed to catch that. I'm glad you did catch it. Does everybody see what I'm saying? So we just needed to have a negative 1 here multiplied to that. So this would be negative sine cubed x. Good catch. Negative sine cubed x. Good catch. Because that is actually something like a lot of mistakes that we make on these. You just get going and mess up. Okay, Okay, here we go. Let's do another one. So number 30, secant squared x times 1 minus sine squared x. So there's so many ways we could tackle this problem. Is there anything, like any ideas of where we should maybe go with this? I like that. Let's change that to what? Yep. So this is secant squared x times by, so this is equal to, times by cosine squared x. Because that is the same thing as cosine squared x. Good, that's exactly right. So now secant squared x is 1 over cosine. So this we're going to rewrite as 1 over cosine squared x. So we have 1 over cosine squared x times cosine squared x. So isn't that multiply straight across? Isn't that how fractions work? So this is your work. You'd show cosine squared x over cosine squared x actually equals 1. So that whole thing simplified to be 1. You would way rather do calculus with 1 than all that. Yes. Yeah, you can still do that. Good question. Why? Can you do that? Oh, okay. I was going to say, I can show you why. Does anybody care why? No? Okay. All right, let's do this one. What's this one? Any ideas? What's tangent squared x plus 1? Secant squared x. So let's rewrite this. This is the same thing as 1 over secant squared x. So then what's that the same thing as? What's the reciprocal of 1 over secant? Same thing as cosine. So cosine squared x was our answer. That's way prettier than dealing with fractions in calculus. Okay? So, like I said, there's not just one way of doing it. Okay, I'm going to ask you a very important algebra question. Could I have split it up and done 1 over tangent squared x plus 1 over 1? No. Nope. We can't split that up. Does that make sense, everybody? That's a common thing seen in calculus 1. But do you understand why you can't? Yeah. Okay, good. Maybe you've seen things. Okay, let's go. Simplify the trig expression. So there's many ways to tackle it. So, many ways. Like some people can come up with a way quicker way than me. Anybody have any ideas? I have many. Okay. Okay, let's do that. So tangent squared of theta is sine theta over cosine theta, right? So I'm going to rewrite that. Divided by, what's secant? Sine squared. Sine cosine squared. Okay, now on bottom, what's secant squared theta? Okay, 1 over cosine squared theta. Dividing fractions is easy as pie. We flip the second fraction and we multiply. So that's going to simplify to be, those divide out, sine squared theta. Because your brain's more developed. Yeah. Okay, let's go for this one. Couple more examples. 38. So we're trying to make this a prettier answer. What's the same thing as cotangent of pi halves minus x? Is it? Yes. Tangent of x. Look at your trig identities. So that's tangent of x times cosine of x. So now your goal is to make it prettier. What's tangent the same thing as? Yep, sine of x over cosine of x. So times, because look at your trig identities. So now what does that simplify to be? Good, those divide out sine of x. So who would have known that that simplified to be the same thing as sine of x, which is gorgeous compared to that bad boy. 40. Okay, guys, take my, well, there's so many ways to do these. There's so many. I was going to say, take my suggestion, and I'm like, oh crap, my suggestion would have made it harder. What do you think we should do? What's that? Secant squared t, guys. So we have cosine of t. I'm going to put parentheses because otherwise it gets too confusing. Times secant squared t. So now let's simplify it. We have cosine of t times. Oh, I made that. I'm going to go a different route because I made it harder. No, I didn't. There's so many ways. Okay, cosine of t times what's secant? The same thing as 1 over cosine squared t, right? No, the answer's not 1. So we have cosine of t because we can multiply straight across over cosine squared of t. Nope. 1 over cosine of t. Does everybody see why? There's 1 cosine on top and 2 on bottom. 1 over that equals, Ethan, secant t. That's why I know to keep going is I'm like, well, like the one answer is much prettier than, you know what I mean? So that's where you're going with these. How about 42? I really just think the more you see, the easier it is. Is that okay with everybody if we keep going a few more? So secant times tangent of, I think that's the lambda. No, what is that called? What's that Greek symbol? Anybody? Somebody look it up on their phone while we do it. Greek symbols. I think it's lambda. That's the lunch bell? Okay, so going with this one, we have cosecant, oh, it was C. Guys, we need to get going. We waste so much time in this class coming back into and from lunch. So cosecant phi, tangent phi plus secant phi. So I'm not even really sure where this one's going. Let's just go for it. What's cosecant? Okay, maybe let's go with that. 1 over sine of phi. Now tangent is sine phi cosine phi over cosine phi plus secant phi. So now I'm seeing where this is going. Don't those divide out? So we have 1 over cosine phi plus secant phi, which what's this? The same thing as secant phi? So we have secant phi plus secant phi. I put theta on accident, but you know what I meant. So 2 secant phis. So that's much prettier. So once you get down to like one thing you're in, that's when you know like I'm probably good. Okay, the reason they're having us factor the expression is so that you can see how to kind of go backwards. So if we were to factor secant theta minus 1, isn't that the same thing as having like, for example, x squared minus 1? Okay, so we're going to do like a u substitution. U is equal to secant theta. So if we have u squared minus 1, we could factor that. Well, multiplies to be negative 1 and adds up to be 0. 1 times negative 1, right? Can I quick factor it? So u minus 1, u plus 1. So this factors, it's not u, it's secant. Secant theta plus 1 and secant theta minus 1. So I just did a u substitution. Because that's just the same thing as u. Does that make sense? This one, yeah, we're just factoring. So it says factor the expression. So same thing here, guys. To factor this, I'm going to say, well, this kind of looks quadratic in form. 4x squared plus x minus 3. So I'm going to say let x equal, I'm going to use x as my substitution. Let x equal tangent theta. So then we're dealing with this. So it multiplies to be, careful, this is long factoring. It multiplies to be negative 12 and adds up to be 1. Can I quick factor it? Heck no. Drop and break. So we have 4x squared plus 4x minus 3x. We're breaking down our middle term, minus 3. Factor by grouping. 4x in common, left is x plus 1. Factor out negative 3, left is x plus 1. Our safe haven's the same, so we can factor out x plus 1. Left is 4x minus 3. But now instead of an x, we need to put tangent. or tangent of theta minus 3. Very good. That was factors form. Okay, so it says factor the expression here. So first of all, it's kind of like, well, where is this going? So let's think. It kind of looks quadratic in form, guys. Look, x squared minus x minus 3, kind of. But that's cotangent and cosecant. That's the problem, though. So let's figure out what's cosecant the same thing as. That still is not helping us. So let's look at a different trig identity that might help us. Yeah, 1 plus cotangent. So instead of having cosecant of x, this is 1 plus cotangent. But we have to be careful because it's actually this. 1 plus cotangent of x squared. No, it's not. You were right when you said 1 plus cotangent squared x, right? So I just replaced that with this. So then we have minus cotangent of x minus 3. So now, do you see where this is going? Hey, over there. Where do you think I should go from here? There's not an equal sign, though. Combine like terms. I like Brooke's idea. Combine like terms. So we have cotangent squared x minus cotangent of x minus 2. So then that's x squared minus x minus 2. So we're going to say let x equal cotangent x. And now we can factor. What multiplies to be negative 2 adds up to be negative 1. 1 times 2, negative 2. We can quick factor it. So this factors to be x plus 1, x minus 2, right? So then we have cotangent of x plus 1, cotangent of x minus 2. Very good. Did I go too fast? No, we're good? Good. Okay, simplify the expression. I think we're probably good with trig identities. Okay, looking at this one, guys, simplify the expression. Here's what we're going to do. If you see that you have fractions, you want to have one fraction. So we would need a common denominator, correct? That's always where you go if you have two fractions. Get a common denominator and put it over one fraction. So I'm going to multiply this by 1 plus cosine theta over 1 plus cosine theta. I'm going to multiply this by sine theta over sine of theta. So now I'm going to show my work. We have sine squared theta over sine theta times 1 plus cosine theta. I'm going to leave it split apart. Plus, I am going to distribute this through. So I have plus cosine theta plus cosine squared theta all over sine theta 1 plus cosine theta. So now you'd say, look, I have a common denominator. So now I can make it into one fraction. Combine the tops all over the same. So we have sine squared theta plus cosine theta plus cosine squared theta. And that's all over sine theta times 1 plus cosine theta. Now let's reorder. Addition can be reordered in any order, can't it? Yeah? We can. So let's take those two and write them by each other. So wouldn't those two become a 1, guys? So we have really on top 1 plus cosine of theta over sine, oh, nope. Yep, because those became 1 over sine of theta times 1 plus cosine theta. Now remember, you can never divide across addition unless it's an entire factor. But aren't those entire factors? So that became a 1. So 1 over sine theta, which is cosecant theta. Who would have known that that would have simplified to be that? Not me, until I did it. The algebra doesn't lie. Okay, how about this one? Here's the thing, guys. You gotta be careful with this one. Let's see what you think. Any trig identities you're seeing? Nope. Nope. Nothing. Nada. Well, we don't want a fraction. That's hideous. So what do you suggest? Anybody have any suggestions here? Yeah? Okay, yeah, there could be some manipulations with some ones. That would be a good idea. You could see what you could do with that. That is not wrong. You could see what you could do with that and see if you could come up with something. That was actually a really good idea. You're on the right total track. Here's the thing. So you are on the right track. You're saying, hey, you too. Seriously? We guys right off. Listen. Okay. Here's the thing. We can't. There's a few things we could do. But here's what we're gonna do. Nah, there's really not a few things we could do. We're gonna multiply by the conjugate, because doesn't that kind of cancel out some things, maybe? Change it. I don't know. You guys tell me. What's the conjugate? 1 minus, kind of like rationalizing the denominator, 1 minus sine of x. So we'll do that to the top and bottom, because you can't just do it to the bottom. Let's change the problem. Now we're multiplying by a fancy 1, so all is good. So we have 1 times all that stuff. So what if we distribute 1 through? So we have on top 1 minus sine of x all over. Let's distribute that. Let's double distribute and multiply out the bottom. Since they're conjugates, the middle term will cancel out. So I only have to multiply 1 times 1, which is 1. Minus sine squared of x. Okay, let's see where this is going to go. The bottom is cosine squared x, right? So we have 1 minus sine of x over cosine squared x. Does everybody understand? Now, isn't it okay, and it is appropriate to split up like this? 1 over cosine of x minus sine over cosine x. Yes, that is appropriate. Nope. Oh, cosine squared. Good point. Yep, it is cosine squared, right? Uh-huh. Okay, let's look at that. So what's this the same thing as? Secant squared x, which is now pretty. And then what's this? Well, let's be careful. Let's think of it like this. So we have secant squared x minus, isn't that piece tangent? So we have tangent of x, but then it's still times by 1 over cosine of x. What's 1 over cosine? Secant. So we have secant squared x minus tangent of x, secant of x. And now we're not dealing with fractions or anything. No, you don't, fractions are not pretty good. What? Yeah, they're different. We could, I think this is where we're going to end. But I'm seeing like, well, we could factor out a secant x, right? Yeah. Because there's a secant in each term. So then left would be secant x minus tangent of x, which is just about the same. Yes. But it's not squared anymore. Oh. Oh, I see what you're saying. Oh, I see what you're saying. Yeah, but then you're dealing with tangent factor. You know what I mean? I think this is as far as we go. Because now we're not dealing with fractions. In fact, that is how far we go. I remember. Yeah. Yes. No. Integrating fractions and doing calculus of fractions is always a nice command. Good question. So I see where you're trying to go with it, but do you see if you did try to factor it, like you'd have a tangent still though? You have secant, so you could still. What do you mean? Oh, like this you mean? Or like this? They're equally, I would want it, like calculus, you'd do that. Okay, so it says use substitution. We're down to our last few examples here. Use substitution, x is equal to 2 tangent theta. If theta is between 0 and pi half, so we got to take that into consideration. Wouldn't that be in this quadrant, guys? 0 and pi half, so tangent is here. So doesn't that mean that sine is positive and cosine is positive? Positive, positive. So we have an x, y point that's both positive. Okay, so it says to write this as a trig function of theta. So we're going to substitute, and instead of an x, write 2 tangent of theta. So we have the square root of 4 plus all of x, so that's 2 tangent of theta, all squared. So let's simplify that. That's the square root of 4 plus 4 tangent squared theta. Because isn't this squared and that squared? So now we have the square root. Isn't there a 4 in common? Pull out a 4. Left is 1 plus tangent squared theta. So what's the square root of 4 times the square root of 1 plus tangent squared theta? So what's the square root of 4? 2. Now can I square root that and square root that? No, that's breaking the forbidden rule. But we can if there's only one square. What's that the same thing as? Secant squared. So we have 2 times the square root of secant squared theta. So isn't that, cancel out with that? 2 secant theta. Yep. Just taking it and simplifying it in the prettiest form possible. Okay, last example, and then it's the homework. What? No, I didn't say graph it. It's just saying that sine and cosine are positive. Okay, so it says write as a single logarithm and simplify. So we're going to use what we just learned and tested on, properties of logs. So if you're multiplying, you do what? If you add, I mean you. So we have cosecant theta times tangent theta. So we can put them in the same ln. So let's simplify that. ln of cosine theta, tangent is sine over cosine, right? Cosecant theta. So then we have this. Okay, so we have ln of 1 over sine of theta times sine of theta over cosine theta. So since it's multiplication, we can just divide out our signs. So we have ln of 1 over cosine theta, which is what? Yep, so ln of the secant of theta. And we know it's pretty because now we're not dealing with fractions. We have one answer. We're all good. Cosecant? No, wait. Because I wrote cosine, not cosecant. So, like, that wasn't even a good, the whole time it should have just said cosecant. Because see how this says cosine, but we really should have had cosecant. That's the homework. We only have not that much time. You have till 12, so you have 20 minutes. So start practicing, and then it really just, you'll see, once you get good at these, you get good at them. Like you can see, I don't even, like, I just trust my instincts at this point, you know what I mean? You'll get to that point.